Welcome to this explainer. Today, we're getting right into a zero-fluff, high-signal breakdown of the core directive film, or DTF, printing hardware stack. We all know DTF has completely shifted apparel decoration, right? But to really leverage it, we've got to strip away the noise and look strictly at the mechanics. Our objective today is super simple. We're going to visually map the physical hardware stack and establish the absolute baseline for operational efficiency. We're tracking the exact physical journey, literally from the digital file all the way to the finished garment. Let's dive in. Okay, here is the absolute core paradigm shift for this entire process. Success requires a continuous process, not isolated machines. Look, far too often, print production pros look at their floor and they just see a printer, a shaker, and a press as completely separate entities. But to achieve actual operational efficiency, you have to treat DTF as an interconnected, continuous manufacturing line. Mastering this baseline flow, moving smoothly from one machine directly into the next, that's exactly how shops reduce variability and actually protect their margins. So, here's our roadmap for today. We're tracking the product precisely through 4 sequential stages. Step 1 is the brain. Step 2 is the engine. Step 3 is the catalyst. And finally, Step 4 is the execution.
Kicking things off with Step 1, the brain, the 𝗶𝘁 software.
The manufacturing process actually begins long before a single piece of hardware moves and way before a single drop of ink even hits the film. RIP stands for Raster Image Processor. Simply put, this is the software that dictates the exact volume of CMYK and white ink that's going to be laid down. A lot of shops think their profit is made over at the press, but honestly, proper pre-flighting and RIP configuration are where a shop actually establishes its margins. Think about it. If the brain is sending the wrong signals, the rest of the body, meaning your physical hardware stack, is going to fail no matter how good your machines are.
So, those signals from the 𝗶𝘁 software dictate your exact ink volumes. And accurate ink limits are absolutely vital because they completely prevent ink pooling on the film. Plus, dialing this in ensures your white underbase actually supports the color without any bleeding. You're essentially building a microscopic, perfectly calibrated foundation here. Without this precise software control, you're just introducing variability right at the starting line.
Moving right along to Step 2, the engine. That's our printer.
This is where we shift from digital data right into the mechanical output phase, laying ink onto a specially coated PET film. The print file gets sent to the machine, but remember, the design is printed in reverse. Step 1, the CMYK color layer goes down first. Step 2, that opaque white ink layer is applied immediately after, right on top of those colors. It's a very strict sequential output onto that PET film.
Now you might be wondering, why that specific order? Well, that white layer serves a dual purpose, and it is absolutely the critical binding surface for the adhesive. Obviously, this white opaque foundation is what allows your CMYK colors to pop and remain vibrant on dark garments. But mechanically speaking, in the context of our continuous production line, it acts as the physical anchor. It's literally the wet surface that the next phase of our process relies on completely.
Which brings us to Step 3, the catalyst, the powder shaker and dryer. As soon as the wet film exits the printer, it immediately enters this unit and interacts with the adhesive. First up, the unit evenly distributes a polyurethane hot melt adhesive powder right across that wet white ink we just talked about. Next, the automated shaker physically knocks off any excess powder, making sure it only sticks to the ink and definitely not the bare film. Finally, the film travels through a curing tunnel. The heat in this tunnel melts that polyurethane powder into a solid, yet super flexible adhesive layer. So what we're looking at is a highly calibrated chemical and thermal reaction happening right there on a moving belt.
The core operating principle here is that standardizing this thermal step is what leads to reduced variability and prevents peeling down the line. It's a delicate balance. If the dryer is too hot, you damage the film or the ink. If it's too cold, well, the polyurethane doesn't fully melt and bind. Thermal consistency in that curing tunnel is the absolute key to preventing structural product failure when the garment is finally worn and washed. Simplified execution here makes training a breeze and ensures your product actually holds up over time.
And now we arrive at our final stage. Step 4, the execution, the heat press.
All right, so the transfer has been ripped, printed, powdered, and cured, and it is now completely ready for the substrate.
But execution isn't just slamming a hot plate down once and calling it a day. We have the initial press versus the secondary press. Using a commercial heat press, the initial press bonds the transfer to the substrate. And listen, this must be done under strict, measurable metrics for time, temperature, and pressure. Then, once it's pressed and the film is peeled away, the garment typically gets a secondary press. Why do we do this? Because this final hit of direct heat seals the edges and mechanically drives that melted adhesive deep down into the fabric fibers. Both of these steps are completely vital for the structural integrity of your final product.
This really brings us to the ultimate operational payoff of mapping this entire anatomy. Bottom line, DTF only scales when it becomes predictable. That is the absolute truth for any print production professional. If your machines are treated as isolated islands, you just have chaos. But if you understand exactly how the rip, the printer, the shaker, and the press all interact as one continuous flow, you gain predictability. And predictability is exactly what allows a print shop to scale its operations confidently.
Mastering this continuous anatomy seriously matters to your bottom line. It allows shops to eliminate those frustrating production bottlenecks where work just piles up between machines. It drastically reduces manual touch points, which means far fewer opportunities for human error to sneak into the process. And ultimately, it improves consistency across every single production run. You're no longer just crossing your fingers and hoping a run turns out well. You've engineered a predictable manufacturing baseline. By applying the zero-fluff, interconnected anatomy we've walked through today, literally from the brain of the rip all the way down to the execution of the heat press, you can transform a simple collection of machines into a highly efficient, scalable manufacturing line. So take a hard look at your own floor today. Is your DTF workflow a truly continuous process, or is it really just a collection of machines sitting in the same room?